Can you see my screen?
Yes.
Okay. So firm PV power generation for 100% renewable power grids. And I'll summarize that in 3 words. Solar is big, PV is a big resource. It is getting to be very inexpensive, and most importantly, it's a resource that's available, that can be made available all the time, at night and in winter. So big, if you compare the energy reserves of the planet, you see that solar is so much bigger than the reserves that we have for conventional resources on the right that powers the economies of the world. And it's also much bigger than all the renewables, which happen to be byproduct of solar. So PV can do the job. There is enough. There is more than 5,000 times enough to power our consumption, which is illustrated by that little blue sphere here. So no problem, it's big. It's also getting to be very inexpensive. Photovoltaic is probably the cheapest way today to make a kilowatt hour of electricity if you put PV in the sun. This is the price of turnkey solar power plants, utility scale since I started working in the mid-80s. It's down to below $1,000 per kilowatt today, and it's not going up. It's going to be closer to 300 in 15, 20 years. This is a chart I like to look at. It's published by the Lazard Bank every year, but Bloomberg has something similar where they compare the levelized cost of energy for all resources capable of making electricity. And PV is getting very cheap. On the x-axis is the unsubsidized cost per megawatt hour. If you are used to cents per kilowatt hour, you divide that by 10. And utility scale PV is among the least cost. If I draw a line here, it's considerably cheaper than new plants of conventional generation, gas peaking, nuclear. Everybody's talking about nuclear in Europe, but it's way too much expensive, in my opinion. It's cheaper than coal and even cheaper than combined cycle new generation. It's roughly the same price as fully depreciated plants where you only pay for operational costs. And we are not finished there yet. By 2035, if I take the IEA or Bloomberg predictions, we're going to be right here. And the other resources, the conventional one, are likely to go up if we start accounting normally for their environmental and strategic external footprints. And we have a crying example of strategic externality of late with the Ukraine impact on the gas prices, which are pushing those prices much higher than the Lazard published a year ago. But what about 24,365? Because that comparison is not 100% fair. The conventional resources are dispatchable, available on demand, and PV is run by the weather, so it's not available all the time. PV is intermittent, and what we need on the power grid is something that's firm and dispatchable to meet the load all the time. As a result of that intermittency, PV and wind, for that matter, occupy a marginal position on the grids. What I mean by marginal is this. This is the electrical demand that's happened. That's the one of New York City in winter, but it could be any TSO on the planet. And if I operate PV, it operates at the margin. It still floats on a sea of baseload and dispatchable generation to enable it. And as we grow PV, it remains marginal, and the job of the baseload and dispatchable becomes harder. You need much better forecasts to make sure that everything's balanced, and you need to take care of steeper and steeper ramps, manage the weather. But it's still a marginal approach. You've all heard about the famous duck curves that are growing, started in California, but now spreading all over the planet. And that's only the tip of the iceberg. That's a small part of the problem, what happens within the day. The bigger part of the problem is multi-day and it's seasonal. So this is also New York City load on the left is the PV output on a daily basis, and on the right is the load of the city. And you see that there are big holes to manage. So how do you make that switch? How do you make PV 24/365? So how do you go from the margin to a grid dominance of PV? How do you do that transformation? So physically, it's conceivable. You have to transform PV into load shape. So you have to make the yellow into black. The black is the load, the yellow is the resource. And energy storage in a physical sense works for that very well. When you have excess, you put it into storage, and when you need the power, you take it back from storage. Storage technologies are evolving pretty fast, and I like to regroup them. Here it's a plot of power and discharge time for all storage technologies that we could identify, and I like to regroup them into three major groups. The big one, macro mechanical, like compressed air and pump storage, hydro, all the way to the right, PHH. In the middle range, you have all the electrochemical, aka batteries, and then you have the fast response units that only provide power for a few minutes or seconds, like flywheels and magnetic storage or supercapacitors. And I will single out lithium ion, which has been growing very fast and getting cheaper, and everybody predicts it's going to get much, much cheaper. So it's on all your smartphones, your laptops, and now in most electric cars, that's what it's based on. So it's evolving really fast. But as inexpensive as it expected to be 20 years from now, it's still going to be too much to do the job of transforming on a yearly basis PV to firm dispatchable. So we know the intermittent PV is very cheap from the Lazard reports, but making it 24/365, even if I project the cheapest cost that I can in terms of projection for lithium ion in 20 years from now, it's still going to be too expensive. It's going to be very expensive to make a kilowatt hour. And all the difference is because I need so much long-term storage to do the job. But if you think a little bit outside the box and you do something that has been counterintuitive and that's been an anathema in PV deployment business until very recently, if you build more solar than you need and you curtail a good fraction of it, you throw away some of the output, then something interesting happens. Here on the x-axis, I have the amount of oversizing of the PV, so the part that I'm not going to use. You see the firm power, the white line, the LCOE goes down, reaches a minimum. PV goes up because you oversize it and you're not monetizing the entire PV, but the cost of storage can go very, very much down until you reach a point that's almost manageable, where you can actually consider, yes, I can do it. I can do 100% PV because I'm much, much cheaper than if I don't think outside the box. That overbuild and curtail is so effective that we started calling it implicit storage, and many others are calling it that way as well, because it does the same job as storage. It's a catalyst to storage technologies and can do it much, much cheaper. You will still need storage. You don't eliminate it. You need it for night, but you can minimize it. And the press, this is an article from Quartz Business Review, is catching up on it. And they quoted us, solar energy is so cheap that it can be wasted. They should have written, it must be wasted, not can. It must be wasted if you want to reach the least cost. And I'm going to illustrate that quantitatively with two projects we completed. One is for the Mid-Continent System Operator. That was a US Department of Energy contract. And another one we're just finishing now, just north of us, north of you guys, very close, in Switzerland, financed by the Swiss Federal Office of Energy. So MISO first. This is the MISO TSO. It's a very large region ranging from Louisiana and New Orleans here all the way to Minneapolis and the Canada border. Here you have the Great Lakes. Here you have Chicago, which is not into MISO. It has its own little pocket here. And this is the solar resource in the region. So highly variable from north to south, much sunnier in the southwest than in the northeast. Pretty much like Europe. You would have a similar gradient in Europe from Italy to Germany. And that study was called Minnesota Solar Pathways and financed by US Department of Energy. The objective was to analyze whether we could do 100% renewables with an optimum mixture of PV and wind. And wind as a very different resource, also very much like Europe. Wind is much, much stronger in the north than in the south. We looked at the impact of geographic distribution of resource. Do you have to interconnect the whole region to get a cheap price, or can you live by with smaller regions? And we looked at the impact of the technology costs, how the cost of PV, wind, and storage influence the bottom line. And we looked at, I'm going to show two of the extremes that we looked at, near future, with low technological development, with PV at a little over $1,000 per kilowatt, so pretty much what it is today. Wind at $1,500 per kilowatt, and storage at $175 per kilowatt, which is pretty much the cost that Chevrolet and Tesla currently pay for their batteries in their cars. At the other extreme, we looked at the distant horizon, 2050, with high technological development, where PV would be at 360 per kilowatt, wind down to 800 per kilowatt, and storage all the way down to 40 per kilowatt hour. So almost on par with the pumped hydro in that respect for the batteries. And finally, we looked at the impact of flexibility. If you were to keep just a little bit of supply side flexibility with natural gas, so not shutting them all off and using them just when you need, how does it affect the bottom line? Some characteristics of MISO, 120 gigawatts, 670 terawatt hour per year. That's just about twice what you have in Italy. There is not much renewable installed. There is quite a bit of wind, 21 gigawatt installed, but very little PV so far in the region. The geography includes 3 macro electrical regions and 10 smaller load balancing regions. The resource is vastly different in those regions. This is Iowa region, where I have the capacity factor. Capacity factor is runs from 0 to 100. 100 we mean the resource is available all the time, runs all the time. 0 means it's never available. So solar has a typical peak in summer in that northern region, maybe a little lower than Italy, but not much lower. Wind is extremely strong in that region. Peaks in winter, lower in summer, but it's a very high. It's called the Saudi Arabia of wind, that Great Plains of America here. Tons and tons of wind. If I go down to the Mississippi River, down to Louisiana, the wind dies off. It's very small. The solar is just a bit higher, but still quite a bit of clouds. It's very flat throughout the year, except maybe in the late winter. So let's focus on one region and work step by step. Let's first do low technological development, short-term future, just PV, and let's not overbuild the resource. Let's try to conserve every kilowatt hour we have. That's the load in that region, and that's the PV resource. So you can see that they are largely out of phase, big shortfall in winter and surplus in summer. And that's what the bottom line would be, 177 cents per kilowatt hour, $1,800 per megawatt hour, way too expensive, totally unacceptable. That's the view. Most people, they stop there. They see this number and say photovoltaic will never work. It's way too expensive. And if they stop there, they're right. But if you just say, now I'm going to optimally overbuild, I can get, even with current prices, I'm getting down to something that's closer to acceptability. It's still a bit expensive, but it's much closer to reality. The contribution of that is all that implicit storage. That green area here is the PV power that is wasted, that doesn't contribute to energetically, but contributes a lot economically. Now, if I use the future cost at 2050 horizon, then I'm getting down to something which is really interesting. I'm getting below 8 cents per kilowatt hour for my firm 24/365 power, which is not bad. And if I do just wind now instead of PV, I get to something pretty similar. The y-axis has changed, I just made it, but the numbers are pretty comparable to PV, and the level of curtailment necessary is pretty much the same. Now, what if I blend them together? If I do an optimal mixture of both, then I'm getting really close to reality at 4.7 cents per kilowatt hour, and I need to curtail quite a bit less. Now, if I were to spread the resources, not in just one region, I interconnect everything, and I do my blending and take advantage of the less viability because of I have a much larger resource. Interestingly, I go down in costs, but not all that much. That's an important finding of that. You gain a little bit by connecting that whole middle section of the US, but you don't gain it's not black and white. Interestingly, the mix turns out to be much more PV if you do that than wind. 80% PV, 20% wind optimally. This is each regions, that's their optimum mix. So I go for 100% PV in yellow to 100% wind in blue. And this tells you the optimum section if I am to interconnect only regionally. So in the south, it's dominant PV for sure, but even sometimes in the way north, where the PV also has the edge, 50-50 in those regions, but in the south, it's over 80% PV, 87-13 here. And the average cost per region is 4.65 kilowatt hour per kilowatt hour, which is just a little bit cheaper than if I interconnect. So regional resiliency is possible without large-scale interconnection, in my opinion. You don't need to rebuild the entire grid to rewire that region. They can work regionally very well and be resilient for that respect, just with a small premium. Now, what if I bring some flexibility with the supply side natural gas to use just when I need it? Then I really make the numbers much better. So 95% jump from 100% to 95% renewable is very economically strong and effective. I get down to cheaper than the price on that TSO today. That's one of the cheapest in the US because they use tons of coal today. They don't pay for the externalities. I think the TSO price average between 3 and 5 cents per kilowatt hour, and we can get below that with almost full PV and wind. So the key takeaways from that MISO study is that the intermittency at ultra-high penetration can be overcome economically with an optimized technological portfolio, including an optimal blend of wind and PV, application of storage, both real, but most importantly implicit, aka overbuild and curtail. Large-scale interconnection is cheaper, but it's not indispensable. Smaller subregions are slightly more expensive, but provide resiliency benefits and are likely to be much easier to implement. Seasonal storage is not required. That goes under the grain of planning that I hear in the US and also in Europe. You need seasonal storage. In that case, we found out you don't need them. You only need a few hours worth of battery storage to supply the output when you need it. Bottom line is that you can do 4 to 5 cents per kilowatt hour for nearly 100% renewable 24/365 electricity in central US. Now let's move to Switzerland. So this was paid for by the Swiss Federal Office of Energy, and we worked together with Meteo Test from Bern on that. The objective also is to explore 100% renewables, but in that case, that would be more solar and hydro. because you cannot develop all that much wind in Switzerland, so they cannot take advantage of that natural out-of-phase relationship between the two resources. All we have to work is hydro, and they have good hydro. We also explored the impact of PV and storage costs, technology costs, and the impact of also bringing flexibility with some dispatchable generation. So that's the PV resource in Switzerland. So this is actual. It's all the systems in Switzerland operating on any given year. They have a tough job because the difference between the summer and the winter is almost 1 to 8. So they have a very difficult case to make with almost no PV resource from November all the way to March. So tough job. That's the current dispatching of energy on the Swiss grid. I run here a 15-day average, so you can see I remove all the spikes up and down. So that's a 15-day running mean. So the top represents the load on the Swiss network, so it's winter peaking. And the two big suppliers of energy on the grid are nuclear, almost 35% of supply is nuclear, and hydro. And the rest are very small. There is a bit of natural gas, there is some existing PV, and there is some biogas. Plus that grid imports quite a bit of power in the winter season, not enough generation, and exports quite a bit of power in the summertime. Most of it, a lot of it comes to Italy to the summer peaking Italian grid. So that's the current situation. Hydro is just a word about it, because it's very effective for the PV to grow the PV. So there is run-of-river hydro, quite a big chunk of it. This one cannot be modulated. You take it as it's run of the river, so you just have to take it. There is a substantial two-way pumped hydro system, 50 gigawatt hours worth of pumped hydro. And there is a big one-way buffer hydro system. So there are lakes that they can be dispatched on demand, and that's quite a large quantity of energy that they have in these lakes. And it will help PV tremendously in that case. The objective we're analyzing for 2050, full nuclear phase out, so no more nuclear, so find out 33% of the generation and replace it by something else, and at the same time add another 30% to the load due to electrification. So it's a double whammy. You get rid of 30% on one hand and you add another 30% on another hand. You cannot do that with wind because there is not much space to develop wind, just only a little bit. And you cannot grow the hydro. You have to take what is here just a little bit. You can make the barrages just a bit higher, but at most you're gonna grow the hydro by 5 to 10% of what it is now. So the job is on PV to do the difference. So can PV do it with that shape? Well, let's look. These are explored 6 scenarios. So this is the current situation on the left in terms of energy generation. So the big hydro and nuclear today. And in the 6th scenario, the load will be higher by 30%, and the big ones will be hydro and firm PV power. That's that yellow part here. The difference between the 6 scenarios is that gray area, which will be a variety of non-dispatchable like wind and dispatchable resources like natural gas, biogas, e-fuels, very important, and I'll get back to that. And some scenarios also count to the larger European grid to generate power from them. But I'll focus mostly on that 100% renewable scenario that has wind, biogas, and e-fuel thermal generation. So e-fuel is regular fuel like methane or methanol that's made purely with PV, hydrogen, and carbon capture. So, but it's highly flexible. We have 2 technical cost assumptions for the renewables: small-scale systems at 860 Swiss francs per kilowatt, roughly the same as a euro or a dollar, and
$330 per kilowatt hour for battery storage. And then we have a large-scale utility scale system at the other hand with much cheaper price for PV and storage, comparable to the US long-term numbers that I showed in the MISO. These are the other inputs to the economic optimization. So we have e-fuels, very expensive generation e-fuel, 20 cents per kilowatt hour. We have biogas, quite a bit cheaper. It's already running at that price, and wind, quite expensive in Switzerland, 12 cents. But there is not much wind to speak of. It's only that white area, so tiny fraction, that gray space here. And we are looking at two interconnection configuration for the grid. One continues to be interconnected to the larger European grid, but with net zero import, export, except in those scenarios. And another one, which we run the grid totally cut off from the rest of Europe. It's an autonomous fortress Switzerland. Like no more connection, operate standalone. And this is the bottom line. I'll go right to the costs. So in red, I have the small scale system results, and on the blue, I have the utility scale systems. On the 6 scenarios on the left are for the net zero export import interconnected grid, and the ones on the right are for the standalone Switzerland. So they are a little bit more expensive, but not all that much. And all the scenarios are way below 10 cents per kilowatt hour generation, and the best ones are near 5 cents per kilowatt hour, which is not bad for 100% renewable. As a comparison, this was the average on the TSO in 2022, largely because of Ukraine, 23 cents per kilowatt hour day ahead and spot price. 2 years ago, it was running between 5 and 7, so it's on par with the good times on the grid and much cheaper than the situation today. This is the new PV capacity that would be required for each scenario, and I have a green line here that shows me the maximum that's deployable on the Swiss territory. That was part of an older study that had been done by the Federal Office of Energy by looking at every space that could be deployed, like roof space, agrivoltaic on a fraction of the farms, using all the exclusion zones they can find along highways and things like that. So the good thing is that all of the scenario except one fall well within that deployable margin. So physically it looks feasible, and this would be the optimum curtailment, the amount of PV power that would have to be thrown out, not used in each of those scenarios. So for some scenarios, it's very little overbuild and curtailment. Some others, especially the fortress Switzerland, the standalone Switzerland, you'd have to throw out quite a bit of the output. These are those sweet spot curves that we developed for every scenario. I'm not going to dwell on that, but each scenario was determined to reach the optimum solution. This is the current dispatch situation, and that would be the future dispatch situation in that 100% renewable scenario. This would be the net zero interconnected grid, so import in winter, export in summer. In yellow, I have the PV, and dark yellow, it's PV direct to load. Light yellow, it's PV to load via storage. This, the new hydro dispatch, so it goes from a largely summer dispatch to more now of a winter time dispatch. And this is the important e-fuel part, which is very important in winter time, a little bit in summer for that scenario, but here we heavily rely on that dispatchable resource, that very expensive dispatchable resource. So the key takeaways from that Swiss study are PV can meet the challenge of meeting 30% higher demand while phasing out nuclear, currently supplying 1/3 of the demand. The intermittency ultra high penetration can be overcome economically with optimal technological portfolio, including optimal PV and hydro operation, both storage, just like in the MISO study, real and implicit. E-fuel thermal generation, although very expensive, play a pivotal catalyst role. So it should not be discarded. As expensive as it is, it opens the key to get overall very low cost. Large additions of seasonal storage are not required, and Switzerland could operate standalone at little additional cost. I don't think it will. It's important that it stays connected, especially with you guys and with France and Germany. But if they had to, they could do it without much more cost. So some conclusions overall and outlook. 2 projects with different resource and environment indicate that 100% renewable grids are not only possible, but also would be economically reasonable. Intermittent renewable overbuilding and curtailment, aka also known as implicit storage and flexible renewables, is central to achieving acceptable 24/365 solutions. This configuration, and that's very important, must be enabled with appropriate regulations. Currently, they are not. All the systems developed in the US are developed with the assumptions that you're going to monetize every single kilowatt hour that generates. Self-consumption is a baby step in that direction, but in my opinion, it's very incomplete and only very partially effective. So we have to move way beyond that thinking. And the sooner we do that, the better it will be, because the more unconstrained systems are being built, the harder the job will be for the systems at the end of the day. So very important to do that very fast. The role of the TSOs also will evolve from to the management of intermittent renewables and the management of storage from what they do today, which is to manage markets of dispatchable resource. If you have a grid dominant renewable, the job of bidding on tomorrow technically should disappear. I don't see why. The weather is the weather, and you build a system to handle the weather, wind and solar, and the system takes care of itself. It needs to be managed, and that will be the job of the TSOs, because they have a big view, but they won't call for bids to I want so many megawatt tomorrow at 3 p.m. and you better bid, and then you have that system that gets the price artificially higher and higher. And this one is totally, I think, is the most important. Enable smart system to come online. So we don't